Hello, Math 136 students. This is the final exam review. We're going to be looking at this in two parts, the day one versus the day two. So we're going to be looking at this first example here, which says find the vertical, horizontal, and oblique asymptotes, if any, of the rational function. So when we talk about finding the vertical asymptotes, we need to focus on factoring the denominator to see where we would have undefined values for our function. So if we look at factoring this, we know that if it's a trinomial with an x squared in front, it's going to factor into an x and an x. We need factors of 20 that make negative 12 when we add them together. So think about your factors of 20. You have 1 and 20, so sometimes it's good to make a list. 2 and 10, and 4 and 5. And 2 and 10 will make negative 12 if they are both negative, which does make sense since when you multiply that out, that would be a positive 20. So now any place that is in your denominator that doesn't cancel out with any factor on top will become a vertical asymptote. So we would set x minus 2 equal to 0 and x minus 10 equal to 0 and solve both of those, and these are the equations for our vertical asymptotes. So our vertical asymptotes for this problem are x equals 2 and x equals 10. Now, as far as horizontal asymptotes or oblique asymptotes, you cannot have both at the same time. You either have one or the other, and that is dependent on the degree of your numerator versus the degree of your denominator. If the degree of your numerator is less than the degree of your denominator, then you have a horizontal asymptote at y equals 0. If your degree of your numerator is equal to the degree of your denominator, then you have a horizontal asymptote again, but it is your leading coefficient of the top over your leading coefficient of the bottom. So I just call that 1 and 2. And then if your degree of your numerator is greater than your degree of your denominator, you will have an oblique asymptote, and we find that by doing long division. Now for our class, we only focus on a 1 degree difference in these situations, so ours always ends up being linear, like y equals mx plus b, but they can be quadratic or more, higher, if you have a big gap between your degrees of your top and your bottom. So this one has a degree on top that matches the degree on the bottom, so that means we're in this middle case, and so our horizontal asymptote is going to be y equals, the leading coefficient on top is 5, the leading coefficient on the bottom is 1, so y equals 5. And then we have no oblique, since we had a horizontal asymptote. So we have our vertical, horizontal, and oblique. Number 2 is a similar problem, just different setup for our function. So again, we're going to look at, can we factor the denominator to determine the vertical asymptotes? So if we factor this into x and x again, factors of negative 18 that make positive 7 would be a positive 9 and a negative 2. So that means my vertical, and well, we need to check on the top as well. If I pull a 4 out of the top, this is 4 times x minus 2. So notice the x minus 2 does cancel in this case. That would be what's called a hole if we were going to graph this. So hole is when you have canceling of a factor. So we only have one vertical asymptote in this case, and that's going to be solving this, which would make it x equals negative 9. Now, in terms of horizontal or oblique, we need to again look at our degree of top and bottom. Degree on top is a 1, degree on the bottom is a 2, so the top is smaller than the bottom, which means it is horizontal, and it is y equals 0. That is the x-axis. That's because you can't divide x squared into something that is smaller. So that's why that is 0. So there are the 3 answers for that one. So now let's move on to number 3, which has us actually sketch a rational function. And to sketch a rational function, we like to point out all of the different things we've learned about rational functions. So things that we know is we can find the domain of the function. We can figure out if it has any vertical asymptotes, horizontal asymptotes, oblique asymptotes. We can determine if it has x-intercepts or y-intercept. And we can also determine if the function has a hole or not. So the first thing you want to do is factor anything, if you can, on the bottom. This is an x minus 4. That's a single degree there of 1, so unless there's a GCF, there's nothing we can do. So that means that is going to be a domain issue for us. Anything in the denominator, whether it's a vertical asymptote or a whole, if it makes you divide by 0, it's a domain issue. So in my domain, I know that x cannot equal 4. That means x equals 4 is also a vertical asymptote. The degree of the top is 0 because there's no x. The degree of the bottom is 1. So this is again one where the degree of the top is smaller than the degree of the bottom. That makes my horizontal asymptote y equals 0. That means I have none for oblique asymptotes. To find your x-intercept in a rational function, you have to set anything that doesn't cancel out on the top equal to 0. But 3 equal to 0 gives me no x's, so there are going to be none for our x-intercepts. The y-intercept is found by plugging in 0 for all the x's, so this is 3 over negative 4. So that's negative 3/4, so that would be as an ordered pair. And because there was nothing that could cancel a factor on top and bottom, there is no whole. So we're going to graph what we know, and then we might have to find a few extra points using a table of values to get just a rough sketch that has enough points to it so we can see what the graph is doing. So just give me a second to put my table together, and we will plot what we know and try to find anything else to help us graph. Okay, so we know that we have a vertical asymptote at x equals 4, so go to x equals 4 and draw a horizontal, or excuse me, a vertical dashed line. So this is at x equals 4. We also know we have a horizontal asymptote at y equals 0, so notice I have to hover a little bit above that so you can see my line, but it technically is on the x-axis. We have a y-intercept at 0, negative 3/4, so that's down here. So now we don't have a lot of points, so what I like to do when I'm missing points is I make a quick little XY chart and plug this into my reduced function. I make sure that I have some points on either sides of any x-intercepts and vertical asymptotes. So we don't have any x-intercepts, so the only thing that can kind of separate us is this vertical asymptote. So I want to pick at least 2 points on each side. Maybe I'll pick 2 and maybe something over here, maybe negative 2. And then I'll pick some to the right of that line, so maybe let's say 6 and 8. We might plot some more points if we don't have enough. In fact, I might do 5 as well since I already have a point on this side. That would give me 3 points on each side. So you just plug this into your function. So 3 over negative 2 minus 4 would be 3 over negative 6, which is negative 1/2. 3 over 2 minus 4 would be 3 over negative 2, or negative 3/2. 3 over 5 minus 4 is just going to be 3. 3 over 6 minus 4 is going to be 3 over 2, so 3/2. And 3 over 8 minus 4 is 3/4. So let's plot these and see if we have enough information and what we know about asymptotes, which is you cannot cross a vertical asymptote at all. We can kind of get the scale of what this is going to look like. And again, this is just a sketch. So negative 2, negative 1/2 is going to be a little bit higher than the one we did over here. Positive 2, negative 1.5. So as you can see, our graph looks like it's kind of hovering on that horizontal asymptote and headed down towards this vertical asymptote because it can't cross that. And then we have over here on this side, we have 5, 3, 6, 1.5, which would be right about here, and 8, 3/4. So notice this one's in the upper corner. Now, if we want to know for sure whether or not we cross the horizontal asymptote, because that's iffy, we know we can't cross the vertical asymptote, there's a quick way to tell. If you take your reduced function, which is 3 over x minus 4 since it didn't reduce, and you set it equal to the value of your horizontal asymptote, I put it as over 1 because I want to see it as a fraction. We can cross multiply here, and as long as there's no, because 0 times anything is 0, as long as there's no x to solve for, that means we won't cross our horizontal asymptote. If we did have an x to solve for, we would cross at that x value on our horizontal asymptote. So that's just something interesting to know in case you're curious. So let's look at number 4. We're going to be finding the inverse of the function f of x equals x minus 3 to the 5th minus 2. So remember, to find an inverse function, we're trying to solve this in the opposite way. So remember, a regular function's ordered pairs x, y. The inverse function would have those reversed. So we want to swap our x and y's in our function and then resolve for y because we want it to be an explicit form. So the first thing I usually do is think of this as the letter y, and then I'm going to swap the x's and y's. So x equals y minus 3 to the 5th minus 2. We're going to try to get the y by itself, so we need to isolate it. So we're going to add 2 over. And then we'll take a 5th root to get rid of that power of 5 of both sides, which will just make this y minus 3. Then the last step would be to add over the 3. So now this new function solved for the y here is our inverse function. So remember, the notation for that is f inverse of x equals the 5th root of x plus 2 plus 3. So we have done the inverse of our original function. Now, this process gets just a tiny bit more involved when you have x's that are repeated on the function. So we have an x on top and bottom. Still the same idea. If we swap our x and y's, this would become x equals 3y plus 4 over 2y minus 5. I like to think of that as x over 1, and I'm going to cross multiply. So this would be a 2xy minus a 5x equals a 3y plus 4. We're trying to solve for, remember, the y, so we need to get them on the same side together. So I'm going to subtract over the 3y and then add over the 5x. Then I will pull the y out as a GCF and then divide it to the other side, because the goal is to get this y by itself, and we had 2 of them once we'd made the swap. So we had to cross multiply to get everything on the same line, group our y's together, pull out the y as a GCF, and then we were able to isolate it. So this would be rewritten as f inverse of x equals 5x plus 4 over 2x minus 3. Okay, for number 6, we're trying to solve this equation. This is an exponential equation. If we can get the bases to match on both sides and a single base on each side, we will not need to use logarithms. If we can't get the bases to match, which we'll see one of those in a little bit, then we do need logarithms to solve the problem. But 64 and 16 both have 4 as a base that can be used. Remember, we are not changing the actual number, we are just rewriting it in an alternate form where the bases match. 64 is 4 to the 3rd power, so that is still 64. And 16 is 4 to the 2nd power. So notice now they're both being written in a base 4 format. Once we do this, we have to use laws of exponents. So this says power power, so we multiply the powers. And that is distributive. So this will be 4 to the 9x plus 6 equals 4 to the 2x minus 2. Now we had a law that said if you have the same base on each side, and there's only 1 on each side, that the only way this can be true is if the exponents are also equal. So since we have that scenario, we can set up 9x plus 6 equals 2x minus 2. We'll subtract over and get 7x. We'll subtract 6 and get negative 8. And this gives us negative 8 divided by 7 as our x value. Okay, let's look at number 7. It says, how much money should be invested today? So that means we're trying to figure out our present value in order to have a goal or a future value of $10,000 in 20 years if the rate is 4.5% compounded monthly. This is a key to tell us which formula to use. Remember, that is A equals P parentheses 1 plus R over N to the NT. So we are looking for the present value. So we're going to plug in what we know, and then we'll isolate P. 0.045. Remember, rate has to be written as a decimal. Compounded monthly means 12. That does not look like a 12. Give me a second. Let's fix that. There we go. And then we raise that to the n again, which would be 12 times the number of years, which is 20. We're going to isolate this by getting p by itself. So this is 10,000 divided by 1 plus 0.045 divided by 12. I like to go ahead and work this out. That's 240 for that exponent. And we're going to use our calculator. Now, I always like to round up when you're doing p, and the reason for that is because you don't want to undershoot your goal. You would rather be over than under. Otherwise, you haven't met the goal. So I always round up regardless of whether or not there's a 5 after the digit that I'm going to. I don't know that everyone does it the same way, but that's just typically how I feel. If you're going to meet your goal, you need to actually round up and meet the goal, because undershooting will not meet your goal. And then this is to the 240th power. So 10,000 divided by, parentheses, 1 plus 0.045 divided by 12 raised to the 240th power. And I'm getting 4,072, and this naturally rounds up, but I would have made that a 55 no matter what, just to make sure I get that goal. So 4,072.55. If they said to the nearest dollar in the directions, which they didn't, I would round this to 4,073. Okay, let's move on to number 8. It says sketch the graph and dash in any asymptotes for f of x equals e to the x plus 3 and then plus 1 at the end. We have to plot at least 3 points. I'm going to get my calculator cleared because we'll need it in a minute. This is an exponential function. We graph those just really easily by using a table of values. I like to point out that anytime there's something in my exponent, I always make sure I know what would make that equal 0. I want that to be the center of my table of values. It just makes everything nicer. So I'm going to put a -3 there, and then I need to pick 2 numbers that are smaller and 2 numbers that are larger. We may not plot all of these, but we're going to work them out. So e to the -5 plus 3 and then plus 1, e to the -4 plus 3 and then plus 1, e to the -3 plus 3 plus 1, e to the -2 plus 3 plus 1, and e to the -1 plus 3 plus 1. So this is e to the -2, since we're going to add those 2 exponent parts together. Now, you'll have to forgive me, my calculator requires me to enter in the exponent first. I know yours probably doesn't, but I want to make sure we get all of our correct answers. Then we're going to add 1 to that answer. So 1.14 is our first y value. Then we're going to do e to the -1 because I'm combining my exponents. And then plus 1. That is 1.37. This is e to the 0, which is 1, plus 1 would be 2. This will be e to the first plus 1, which is 3.72. And then this is e to the second plus 1, which is going to be 8.39. So we are going to graph, and remember we also have to sketch in our asymptote. Exponential functions have a horizontal asymptote, and it is directly related to the vertical shift of that function. So it's going to be at +1. Now we could have graphed this strictly by transformations if we knew the graph of e to the x, because it's just been shifted left 3 because of the +3 in the exponent, and up 1. So this is -5, and then 1.14, -4, 1.37, -3 is at 2, -2 is at 3.72, and -1 is at 8.39. So 1, 2, 3, 4, 5, 6, 7, 8.39, little less than half. So notice this is an exponential graph, but it is hovering not on the x-axis like they normally do for us, but right at the line y equals 1. All right, let's move on to number 9. It says you have $5,000 to place in a CD, for 5 years. The CD pays 3.6 annual interest compounded continuously. So that is our PERT formula. And then how much will the CD be worth at the end of the 5 years? So we have $5,000, that's our principal. We're going to be putting in interest of 0.036, change to a decimal, and for 5 years. So this is strictly going to be plug and chug. I like to go ahead and know what my exponent is. That's just personal preference. Makes it easier to type into the calculator. So it's a 0.18. Just a little bit quicker to type in because you don't want to round early on any of these problems. You want to make sure that you get the correct answer. I do not clear out my calculator. I just work out the E and then times it by the 5,000. And depending on what we're rounding to, which I don't see any directions on that, I'm going to go to 2 decimal places here. And then I round normally when I'm solving for A. The only time I disregard my rounding rules is when I'm solving for P, which is a present value. So this is 5,986.09. If we're rounding to the nearest whole, it would just be 6, 5986. So $5,986.09. That is our A. So we've earned, in that 5 years, we've earned $986.09 in interest. So that's nice to know. Okay, for number 10, we're finding the domain, range, and asymptote of the given function. This is a logarithm. Logarithms have vertical asymptotes, and they have a range that is always negative infinity to infinity because it's the opposite of what you see in the exponential. They're inverses of each other. The domain and the vertical asymptote are both dependent on the inside argument of the log. What I mean by that is this x plus 5. Has nothing to do with the -1 or the 3. So for our domain, you need to know that, remember, logarithms are restricted after, you can't plug in log of 0 or anything like that here. This has to be greater than 0. You can't have a log of a negative number in your argument. So we know that to make this happen, we have to set x plus 5 greater than 0, not equal to. So we know that it is -5 to infinity. That's why I don't use brackets here. The range for a logarithm is like the domain of an exponential. Since they're inverses, it is any number possible, so all real numbers. And then the vertical asymptote is what value is making us, where would we have an undefined pretty much logarithm, which is when it would equal 0. So that's at -5. So x equals -5 is our vertical asymptote. Okay, moving on to number 11. This is solving a log equation. When you have logs intermingling with things that don't have logs attached to them, the goal is to get all the logs on one side and then use the spiraling or conversion to exponential form to solve the equation. I call it the spiral just because I draw a spiral. So we're going to subtract over this log of x minus 2 to the other side because it is keeping me from getting that 2 away from the logs. Now I'm going to use the rule that says if you have subtraction and your log bases are the same, you can combine it to a single log, but the arguments become division. So it's an x plus 3 over an x minus 2 equal to 2. And we don't have logs on both sides, so we can't set the insides equal because there is no log on the right side. So we have to remember this is a base 10 when you just see the log. So this is 10 to what power, which would be 2, equals the argument. So 10 squared equals x plus 3 over x minus 2. That's 100 equals x plus 3 over x minus 2. If we cross multiply, that'd be 100x minus 200 equals x plus 3. Subtract the x, that's going to be 99x. Add the 200, that's 203. So this is 203 divided by 99. Okay, let's look at number 12. Same type of situation. This does not have a log, so we have to make sure we combine, but this time at least the logs are on the same side together. So we're going to combine them with the rule that says if you have logs of the same base and there's a plus between them, you can multiply their insides, their arguments together. So this is going to be x plus 4 and x minus 2 multiplied together. Notice our 3 is still there on our base, and we have our 3 on the other side. So this is log base 3 of x squared. That'd be a 4x minus a 2x. That's plus 2x minus 8 equals 3. Again, this side does not have a log, so we have to do the conversion to exponential form. So 3 to the third equals x squared plus 2x minus 8. And this is 27 equals x squared plus 2x minus 8. We would move over the 27. So that's going to make that negative 35. Factors of 35 that are different signs and add to 2 would be a positive 7 and a negative 5. So we get two possibilities for our solutions here. And I am going to go back to the previous problem because I forgot to mention something. Your answer to your logarithm has to be checked. So let's go back and do that really quick. The inside argument has to stay greater than 0 for all logs in the original equation. So 203 divided by 99 is about 2.05. That's a rough estimate, of course. So if I add 2.05 plus 3, that is definitely greater than 0. 2.05 minus 2 is definitely greater than 0. So notice this is still going to be positive, so that means that answer is okay. The reason that's important is because remember there are domain restrictions for logarithms, and you'll notice that when we go to check these, negative 7 plus 4, because we need to make sure both of these arguments stay greater than 0, is not true. So as soon as it fails even just one of the arguments, it's out. So let's check 5. 5 plus 4 greater than 0, check. 5 minus 2 greater than 0, check. So the only solution, because of domain restriction, is positive 5. So let's look at number 13. This is an exponential equation, but before you can solve it, you do have to have the exponential piece kind of by itself or isolated. So this 5 to the 2x, because that's where I'm trying to get, is this 2x is what I'm trying to solve for. We need to get the 4 out of there. You cannot multiply them together because this has an exponent on it. So this is going to be divide both sides by 4 first. So this is 5 to the 2x equals 6. And notice you can never make 5 and 6 have the same base. So what we do is we take the log of both sides because that allows us to use some of our properties. And that is legal as long as we use the same log base on each side. So the power rule says that if we have a power on our argument, we can bring it to the front of the log as a coefficient. And then we can divide both sides by the 2 and the log 5 to get the x by itself. And there are other ways to approach this, but this is just using that log base 10. And the reason I like this method is because it is easy to type into your calculator. So this is the exact answer. We want the approximate as well. So here's my exact. And now I'm going to use my calculator to help me get the approximate. So I need to use the log button. So I have to enter my argument in first. Most people have a calculator that allow them to do that differently and do log 6. And then we're dividing by, I'm going to put this in a parentheses because there's two things in the denominator. 2 times log 5. So again, I have to enter my 5 first. Close the parentheses, and this is 0.56 if we go to 2 decimal places. Okay, 14 similar, except this one doesn't have anything to isolate. The problem here is that these two bases will never match. So we can use the log of both sides, and you can use ln if you want. You just have to use that button on your calculator, but use either log or ln, especially since we're usually going to have you calculate these as an approximation. Now on this one we don't, we just want the exact answer. So we're going to pull the 2x to the front. Be careful with the x plus 1. When you pull that to the front, it's a binomial. You're going to have to distribute the log 5 to both of those. So this is 2x log 3 equals x log 5 plus just a log 5. Two of my terms have x's, so I'm going to get those on the same side by subtracting x log 5 to the left. And then we can pull the x out just like we did before on the inverse problems. And then this is equal to log 5 still. Now, we're going to divide this over, and this is where we allow you to stop. Your instructor may or may not have made you go further. but this is where we stop kind of for the answer key. You can also, though, you could convert this by moving the 2 back in on that 3, and you would then also use the rule that subtraction can turn it back into a division, and then you could actually use change of base to convert this to a singular log. So there is more that you could do, but this is sufficient for most of the instructors. Just pay attention to the directions your instructor has given you. If they say you must go further, then they want to see the whole thing and they want you to work it out, and that's okay. But I'm not going to work it out since I believe this is where we stop on the answer key. So Tamika borrowed $5,000 at 9% compounded continuously, so we know what formula we're talking about. Find the time required for the amount to double. Okay, so we have to double our money using continuous compounding. Approximate to 2 decimal places. So we know we're using the PERT formula. Now, if you want to double the 5,000 and make it 10,000, you can put that in here. But essentially, this is just going to end up being a 2p, because even if this money wasn't given to you, doubling p means 2 times p. But we're going to put in what we know. We know it's $10,000 and $5,000, and it's to the 0.09, and we don't know t. So the first thing I would do is probably divide the 5,000 over. Anytime you're doubling your money, you should always get equal to 2 on one of the sides, because that is the factor of multiple of 2. If I was taking half of something, I would end up getting a half over here, so like a half-life. And then this is a problem because what we're solving for is in the exponent. So because there's an e here, I'm going to take the natural log of both sides instead of using log base 10. And there's a really good reason for doing that. So if you pull your 0.09t to the front as a coefficient, you then get times an ln of e. ln already has a base e, so this says e to what power equals e. ln of e is always 1. So that is a fact that is good to know, and that's because there's that hidden base there. So this just ends up being 0.09 times t. So the only thing we need to do to solve it is to divide by the 0.09. Now we want to approximate our answer to 2 decimal places, because you're not going to tell someone the year, the number of years is ln of 2 divided by 0.09, although they would probably laugh and think you were crazy if you did. So ln of 2 is 0.69314, blah, blah, blah. So we're not going to clear that out. And then we're dividing by 0.09, and we're going to round to 2 decimal places, so 7.70. So t is approximately 7.70, and we need our units here, years. So this person would have to let their money set for almost 8 years to double it. Okay, number 16 is a half-life problem. So it says a drug eliminated from the body through urine, suppose for an initial dose of 75 milligrams, so notice that's in front as the P. The amount A of T in the body T hours later is given by A of T equals 75 times 0.8 to the T power. What is the half-life of the drug? So half-life means that in the future, A of T is half of your initial amount. Well, our initial amount was 75. So half of 75, which is going to be a decimal, is 37.5. Now again, I know it's going to end up being equal to a half because we just talked about that on the doubling, but we can plug it in and show how to work the problem. So this would end up being 37.5 divided by 75 to get the 0.8 by itself. And that is a half, because we know that, equals 0.8 to the t. You could use either natural log or base 10 log here. I'll use natural log. Doesn't matter. We would pull the t to the front. So this is natural log of 1/2 equals t times natural log of 0.8. I do want to point out that is not a 1 because that's not natural log of e. So we do have to divide it over. So it's natural log of 1/2 divided by natural log of 0.8. So natural log of a half, so 0.5 natural log divided by 0.8 natural log is 3.11. Are we going to 2 decimal places? Yes. So t is approximately, and again, this is time, and it's in years. Or no, it's not in years. It is in hours. Pay attention to your problem. So it is 3.11 hours. So I'll write that over here. That would be horrible if the drug was in your body for 3.11 years. So looking at number 17, we're looking at a problem. This is from Unit 1. This is a review of exponential rules like multiplying powers, multiplying same base, and what do you do with the powers? So we're doing 3 times 5, which is 15. X to the negative 10 times x to the 7th. You would add the power, so I'm just going to write that. We'll work it out in the next line. Y to the 5th times y to the 2nd will be y to the 5 plus 2. So this ends up being 15x to the negative 3, y to the 7th. And remember, we only want our answer to have positive exponents, so we need to move the x to the 3rd to the denominator. So that's a nice simple problem there. All right, simplifying the expression. This means that we don't want to have a complex rational expression, so we don't want fractions on top of fractions. So my first step is to multiply this by the reciprocal of the bottom to clear that out. And then I want to factor anything I see that might cause cancellations instead of foiling all this out. So the top is an x plus 4 of the second fraction times an x minus 4. And that is helpful because the x minus 4s are being multiplied, so we can cancel anything on top that matches with anything on bottom. So this final answer is 3 times x plus 4 over 4x. And then number 19, we are rationalizing a denominator. That means that we don't want the radical to be in the denominator anymore. We use the idea of a conjugate, which means we keep the two pieces the same except we change the sign in the middle. And we are trying to rationalize the denominator. That's why we're using the opposite of the denominator. If we wanted to rationalize the numerator, we would use the opposite here. And we don't do that here because whatever you do to the bottom of a fraction, you have to do the same thing to the top. So we're going to FOIL this out. So this would be square root of x times square root of x. So that's just an x. Then we get a plus 2 square root of x plus another 2 square root of x, and then plus 4. So that's my numerator. On the bottom, I get square root of x times square root of x again, which is just x. I get a plus 2 square root of x and a minus 2 square root of x, which those cancel each other out. And then I get a minus 4. If I combine like terms on top, I have plus a 4 on a square root of x in the middle, and then I have my plus 4 at the end, and then I have x minus 4 on the bottom. You cannot cancel out these 4s because this is a trinomial and a binomial. They're not matching. We can't partially cancel fractions. So this is just our final answer. And that is the end of, nope, it's not, sorry. There is still a few more problems. We have number 20, which is solving a rational equation. So the way to approach this is to factor any denominators first. And then over on the side, you want to make a list of any answers that are not allowed in our equation, which would be anything that makes those denominators divide us by 0. So this would be a negative 3 and a 3. Now the trick we teach you in class is to multiply everything in the equation by the LCD, which is x plus 3, x minus 3. And that's why we have to make this list, so we don't count those answers because we cleared them out. So you can't get negative 3 or 3 as a final solution. So you pretty much just take your problem and you multiply each fraction in the problem, or each term in the problem, by the LCD. So here's my first one. Then I have x plus 3, x minus 3 times the second fraction, minus the x plus 3, x minus 3 times the last fraction or term. Okay, in this first one, both denominators cancel out and leave me with just 4x minus 5. I have my equal sign. And this one, I get a 2 and an x minus 3. I'll distribute in a minute. On this one, I get a negative, because there was a minus sign, a 7 and an x plus 3. So I'm going to do my distributing and then combine like terms. So this is 2x minus 6 minus 7x minus 21. So I have 4x minus 5 equals, that'd be negative 5x and minus 27. Add my 5x over, I get 9x. And then add my 5 over, I get a negative 22. So if I divide by 9, I get negative 22 over 9. And this should be fine as long as it's not a negative 3 or a positive 3, and I haven't made any errors in computations. So there we go. All right, let's talk about number 21. This is a word problem. It says, if it takes a girl 55 minutes to deliver the papers on her route, if her brother helps, it only takes 20 minutes. How long would it take for her brother to deliver the papers by himself? If necessary, round to 1 decimal place. There's a couple different ways to approach this problem. So, you might have a different way taught by your instructor, and that's okay. I like to think of it as fractions of the job getting done per minute. So if the girl by herself, it takes her 55 minutes to deliver the routes on her paper, and we're assuming she's working at a uniform pace, otherwise we can't use the algebra, we would have to think that she does 1/55th of the job per minute. Now, together, because they didn't tell us the boys by himself, it only takes them 20 minutes, so it'd be 1/20th of the job per minute if they worked at a uniform pace. So we don't know how fast the boy is, so we're going to call him 1/x of the job per minute. That's how much he is completing. Now the way this sets up is that the boy and the girl added together should equal their work rate as a combo. Now, if we were opposing each other, like if the girl was putting the papers down but the boy was taking them away, you wouldn't obviously add the fractions, you would subtract them because they would be opposing each other. But they are working together, and so the solo jobs need to work together. So then we would multiply this all by an LCD. So if you don't know what the LCD is, a good quick way to figure it out is to list the denominators. Obviously X is going to be involved, but so the numbers, what do 20 and 55 both go into? So if I list the multiples of 55, we know 55 times 1 is 55. 55 times 2 is 110. 55 times 3 is 165. And 55 times 4 is 220, which I believe that is one that 20 goes into, because we have 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, and 220. So that's the first time that their multiples match. So the reason this is helpful to list it out like this is you know what to multiply by on each fraction now. Our LCD needs to be 220 and an X. So I'm going to multiply each of these by 220X. You also could just subtract this over and flip that fraction, but sometimes people don't see different ways to solve this. I'll show you that in a minute too. 55 goes into 220 4 times, so this would leave me with a 4X. This would be 220, because the X would cancel out. And 20 goes into 220, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. So that would be an 11X. We could subtract over the 4X, that'd be 7X. So we need to divide 220 by 70, and it said round to, or sorry, 7, it said round to 1 decimal place, so 31.4 minutes if he works by himself. Now I want to show you a different way I could have done this. I could have just said 1 over x equals 1 over 20 minus 1 over 55, gotten a common denominator, which means I would have gotten 11 over 220 minus 4 over 220, which would have been 1 over x equals 7 over 220. And then if you cross multiply, you get 220 equals 7x, and that's the same thing. So, depending on your approach, you should still get the same answer, even if you didn't use the LCD method. All right, and then I believe this is the last one for part 1 of this video. So it says 700 people attended the premiere of a motion picture, so that's total number of people. Adult tickets are $9 each, and children were 4. If they collected 3,400, how many children attended? So I'm going to let x equal children, so I don't have to do any back substituting at the end. And then that means that if there were so many children, there's 700 people altogether, so 700 minus x, which is the children, will equal the number of adults. So then the adults were being charged at $9 a ticket, so 9 times the number of adults plus $4 for each child equals 3,400. So this would be 6,300 minus 9x plus 4x equals 3,400. That is 6,300 minus 5x equals 3,400. We're going to subtract. Oh, it's 300. 6,300. That is negative 2,900. Divide by negative 5. So we don't want negative children. So this is going to work out just fine because it's negative divided by negative. And that's 580 children. Now they did not ask me for the number of adults, so I don't technically have to back substitute. But if I did 700 minus 580, that would tell me the number of adults. All right, that is the end of the part 1 for the final review video. Hopefully this has been helpful to you guys, and I will be working on part 2 next.